In this video, you will learn what is an eigenvalue, an eigenvector, and how they are linked to the natural frequency and mode shape in a real-world engineering example. For most dynamic analysis, the shown turning machine can be reduced to a vertical 2-degree-of-freedom oscillator with the masses m1 and m2 connected via the spring K1 and the spring K2 as the fundament stiffness from m2 to the ground. Although this machine can produce a complex, overlaid periodic motion, its dynamics can be easily described via modal analysis, where the natural behavior of the system as a whole is described instead of each degree of freedom individually. This is industrial standard and looks as follows. The system is described by its system of equations of motion, mz double dots plus kz is equal to 0, where the eigenvalue problem, the determinant of k minus omega squared times m, is equal to 0, of this two-mass oscillator leads to two eigenmodes, each consisting of a mode-shape vector, or eigenvector, and the natural frequency, or also called eigenfrequency. For example, the first eigenmode oscillates naturally with 5.03 Hz, with both masses moving in the same direction, but the mass m1 with more or less 3 times the amplitude of mass m2. The eigenvector in general is normed, so that the degree of freedom with the highest amplitude is 1, and the others are scaled relatively to it. Mode 2 vibrates with 6.74 Hz as natural frequency, but the masses move in the opposite direction, or also called out of phase, which is shown with the arrows pointing in different directions. Mass 1 has approximately 7 times the amplitude of mass 2, which can be seen in the eigenvector phi is equal to 1 and minus 0.137. If you want to learn how to apply these advanced methods to interesting real-world engineering problems, check out the first link in the description with free chapters to deepen your knowledge. So here is how we can read any modal analysis results. Each mode of an undamped oscillator consists of an eigenvalue, shear omega squared, but often referred to as lambda, which is the natural angular frequency of the modes, where all masses move in a coordinated and periodic pattern. Then the eigenvector or mode shape describes the relative motion of each degree of freedom in the system, normed to the highest amplitudes and written into a vector. That's all. How mass and stiffness values shape the modal behavior you will find in the following video.